Hi Chem 1211 folks, this is the video for my absence this week. Thank you for watching. I'm going to take you through slide 29 until hopefully the end of the chapter, but we'll see how the length of time goes. And we are going to talk about the process of drawing Lewis structures for more complex molecules. And so we had done a few of these already, but now I'm going to take you through and do a lot of examples here. And I'm going to give you a step-by-step process. So we're going to do two molecules here on the screen and follow through each step. So first one is PCl3 and the second one is C2H4. So for PCl3, the first step we want to do is sum all of the valence electrons for all of the atoms inside the molecule, so that comprise the molecules. So for PCl3, we have one phosphorus, and phosphorus, if we look on the periodic table, contains 5 valence electrons. Okay? And then we have also 3 chlorides. So we have for chlorine is 3 atoms times 7 electrons for a total of 21 electrons. And so if I add up the total number of electrons here, I get 21 plus 5 equals 26 electrons. Okay, so there are 26 electrons in this structure. Let's do the same thing for C2H4. So for C, for carbon, okay, we have 2 of them, and each carbon contains 4 electrons. So that's a total of 8 electrons for carbon. And then for the hydrogens, we have 4 of them times 1 electron each, so 4, so a total number of electrons of 12. Then we move to step 2. So once we know the total number of electrons, now in step 2, we decide how the atoms are connected and draw a structure. So hydrogen atoms and halogens can usually only form one bond because they only have one vacancy until they reach a noble gas-like configuration. A 1s2 fully filled first shell for hydrogen, or a full S and full P for all the halogens. And so those typically cannot be in the center of a molecule. They need to be on the outside to make one connection. So typically what we do is we find the least electronegative atom and we put that in the center. Okay? And these compounds are always written, if you remember back from previous chapter, as the cation-like one first. And the cation-like one is the one that's going to be more like the positive cation, and the anion-like one comes second, and it's going to be more like an anion, so it's going to be more negative. So in the case of PCl3, it can't be chlorine, so we know phosphorus needs to be in the center. So we put a phosphorus in the center, and then we connect it with 3 chlorines. So we get this kind of skeleton structure for phosphorus, trichloride. Okay, then we go to C2H4, and again the hydrogens can't be in the center, so we must have a carbon and a carbon here. And then we have to attach hydrogens, so we get this kind of a structure, so that all those hydrogens are terminal on the outside of the molecule. Okay, so once we have a skeleton structure, then we go into step 3. In step 3, we subtract the number of bonding electrons from the total number of electrons in step 1. So in step 1, we figured out that there were 26 electrons to work with, and we made 3 bonds on the previous side, you can see at the top. So each bond contains 2 electrons for a bonding pair. So we have a total of 3 bonds, so that's 6 bonding. So that means that we have 20 more electrons to add to this structure. Okay, we're going to assign the remaining electrons to the outermost elements, other than hydrogen, to complete their octets. And so effectively, we want to give electrons to those outermost elements that we said were the most electronegative. So if we, again, go to our structure here, we have P in the center, Cl, Cl, and Cl. Now we're going to add electrons in pairs, 2, 4, 6, 8, 10, 12, 14, 16, 18. So we add 18 electrons to the structure by adding them to the valence shells of chlorines. Okay, we come over here to our other molecule, C, C, H, H, H. And again, from the previous slide, we should have had 12 electrons. And we need to subtract out the bonding. So we look at this structure and it has 1 carbon-carbon bond and 4 carbon-hydrogen bonds. So that's a total of 2, 4, 6, 8, 10 electrons that are in bonding. So minus 10 bonding. So that leaves us with 2 electrons to distribute to this structure. Okay, and we can't put them on hydrogen, so we're just going to skip this step. Alright, then we go to step 4. Step 4 says assign any remaining electrons to the central atom. So again, I'm going to redraw this structure here. And I had 2 remaining electrons that need to go on the central atom here. Okay, and then we go to our other structure. Carbon, carbon, hydrogen, 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 and hydrogen, and we had 2 electrons, so we're going to just assign them to one of the central atoms. Sure, we'll put them right here. Okay, then we go on to the next step. Now all of the electrons are accounted for. So in step 5 it says, ensure that the central atom has an octet. Okay? And so if we don't have an octet at one of our atoms, an octet means 8 valence electrons, use a lone pair of electrons from a neighboring atom to make a double bond to the central atom. Okay? And then just as a note, oxygen, carbon, nitrogen, sulfur often make double bonds, so those are ones that you're going to look for. So again, PCl3, we don't need to do anything there, we're good. But for C2H4, we have 8 electrons on one carbon, 2, 4, 6, 8. But on our other carbon, we only have 2, 4, 6. So we're shy 2 electrons for this carbon, and therefore we need to generate an octet by sharing electrons. So we're going to take these 2 electrons and form a double bond to give us a structure like this. Now all atoms in my structure have an octet and everything is happy. So let's go through and do some examples. I encourage you to try these examples, pause the video, try them, and then watch the video to see if your process is correct. Alright, so our first molecule we're going to do all these steps on is CH2Cl2. So first step, we want to count up the valence electrons. So for carbon, we have 4 electrons. And for hydrogen, we have 2 times 1, so 2 electrons. And for chlorine, we have 2 chlorines times 7, so that's 14 electrons. So we add that up and we get a total of 20 electrons. We have 20 electrons to work with in our structure. Okay, so then, second step is we come up with a skeleton structure. So here we're going to put the least electronegative in the center. Chlorine is just below fluorine, so it's fairly electronegative. And hydrogens have to be terminal and can't make more than one bond. So our only real option here is to put carbon in the center. And so we're going to put a carbon in the center, and we're going to surround that by hydrogen, hydrogen, chlorine, and chlorine. Okay. So now that we have this structure, we want to subtract out the electrons that are used in bonding. Okay, so we had 20 electrons at our disposal. We need to subtract out all of the ones used in bonding, which are going to be 2, 4, 6, 8. So 8 electrons have been used in bonding already. So minus 8 electrons for bonding. That means that we still have 12 electrons to distribute to this molecule. And we're going to distribute those to the outermost, most electronegative atoms first. And here, those are going to be the chlorines. So we distribute 2 at a time. 2 electrons at a time. So we would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's all 12. Now we check to make sure everything has an octet. So carbon has 4 bonding pairs, that's 8. Hydrogen has an octet at 2 because it only has 2 electrons in its valence shell, in the first shell. And chlorines have 3 non-bonding pairs and a bonding pair for a total of 8. So this is the correct structure for dichloromethane. Alright, let's do the next example. Let's do some that have charges. So the previous ones were not charged species. Here let's do phosphate ion and chloride. So first we'll do phosphate. Okay, phosphate, if you remember your polyatomic ions, is PO4 3-. So here for our valence electrons, phosphorus should have 5 valence electrons. Oxygen should have 4 times 6 for 24. And then we have extra electrons, so that -3 charge on there is 3 additional electrons, so we have to add in 3. So if we add up 5 plus 24 plus 3, we get 32 total electrons that need to be distributed to this structure. Okay, so we look at our options, and we need to put our least electronegative in the center. So between oxygen and phosphorus, look on the periodic table. Oxygen is closest to fluorine, the most electronegative, so those are going to be on the outside, and the phosphorus is going to be on the inside. So we have phosphorus, and then we're going to connect it to 4 oxygens. Okay, so now we need to go and subtract out our bonding electrons. So we're taking out 2, 4, 6, 8 for the 4 bonds. So that means 32 minus 8 should be 24 electrons to distribute. And we are going to put it on the outside terminal atoms, the most electronegative first, evenly. So we're going to put 1, 2 in pairs, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 24. Okay, so we have all of our electrons now distributed to our molecule, and now we check for an octet, and everything here has either non-bonding and bonding pairs that add up to a total of 8, so everything has an octet. We should be good. Okay, the only thing we want to do here now is to put a bracket around this and indicate that the charge for this species is 3- overall. This says that there are 3 extra electrons distributed around this molecule. Alright, so now let's do chlorite, or chlorite, sorry. ClO2 -1. Okay, so again, we are going to start by counting all the valence electrons for chlorite. In chlorite, we have chlorine, which has 7 valence electrons, plus we have 2 oxygens. Each one has 6 valence electrons, so that's a total of 12. And then we have 1 additional electron for our -1 overall charge. Okay, so this is 7 plus 12 plus 1 is 20 electrons to work with. Okay, now we come up with our structure. So we have chlorine and oxygen. So we want to put our least electronegative one in the center. And so between chlorine and oxygen, actually they're very close in electronegativity, but oxygen is just slightly more electronegative than chlorine. So we're going to put our chlorine in the center, and we're going to put our oxygens on the outside. Okay? So now we subtract out our bonding electrons. So we have -4 for the 2 bonds, so that means that we have 16 electrons to distribute. We're going to put it to the outermost electronegative first, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So filling up the oxygens takes 12, but I had 16, so I still have 4 more to go, so 14, 16. So that's a total of 16. And now I look at this molecule and everything has an octet. We have bonding pairs and non-bonding pairs, so 2, 4, 6, 8 for oxygen, and it'd be the same for the other oxygen. 2, 4 in bonding and 2, 4 in non-bonding for a total of 8. So everything has an octet and everything should be satisfied now. So the last thing to do is draw the bracket around it and put a negative charge indicating that there is a negative charge distributed across this molecule, this charged ionic molecule. All right, let's look at another example, carbon monoxide. Okay, so carbon monoxide, again, 1 carbon and 1 oxygen, if you remember your naming rules. And so we want to first count up the valence electrons here. So for valence electrons, carbon has 4 valence electrons plus oxygen has 6, so there are a total of 10 electrons to distribute across this molecule. Okay, so we have a skeleton structure. There's no central atom because both of them are terminal. We have 2, and we're going to subtract out 2 for bonding. So that means we have 8 electrons to distribute. Okay, so now we have to decide how we're going to distribute electrons across this molecule. So first we want to put as many as we can around the electronegative atom first. So here oxygen is more electronegative than carbon, so we're going to put our electrons here first. So 2, 4, 6, but we still have an additional 2, so we put the other 2 on carbon. Now we want to make sure that everything has an octet. So if we look at this molecule, again, we have 2, 4, 6, 8 for oxygen, so that works. But for carbon, we just have 2, 4, so that's not going to work. And so our strategy here is to share more electrons. So we take lone pairs of electrons on neighboring atoms and start to create double bonds. And in this case, we have to create a triple bond to get this kind of a structure over here. And we have carbon, triple bond oxygen, this. Now we have 2, 4, 6, 8, and 2, 4, 6, 8. Everything has an octet. Everything is happy. We have a triple bond. We have 6 electrons in bonding here. All right, so now we want to look at formal charges. Sometimes we'll create molecules where we need to decide where electrons are going to go or where a double bond is going to go. So if we look at, in the case of ozone here, okay, ozone is O3 molecule. And when we come up with this structure, we have to make a choice. So if you look here, we would have not had an octet at my central oxygen, and we would have needed to take a lone pair from one or the other oxygen. And so here we need to decide where this charge is going to go. So how we do this is with formal charge. So in formal charge, we take the number of valence electrons. Okay, so the number of valence electrons here, and for an atom, so we look at one specific atom, and then we subtract out 1/2 of all the bonding electrons. Okay, so for any bond, we take half of the electrons in that bond and distribute it to one atom. And we also subtract out the number of non-bonding electrons. That tells us how many electrons are formally around each atom in the molecule and tells us its charge, okay, the formal charge on that molecule. So if we do it in the case of the first oxygen on the leftmost, okay, I'm going to do it in each of these boxes here. Okay, so here I take the number of valence electrons in the free atom. Well, that is 6 for oxygen. And I'm going to subtract out half of the bonding electrons. So here in this molecule, we have 4 electrons in bonding for a double bond. And we also subtract out the non-bonding electrons. Well, there are 4. There are 2 pairs of non-bonding electrons. So 6 minus 2 minus 4 is 0. So the formal charge on that first oxygen is 0. Okay, let's look at the second oxygen. We should have 6 again. We're going to subtract out 1/2 of the bonding. Here there are 3 bonds, so that's 6 electrons, minus the non-bonding pairs, which are 2. So we have 6 minus 3 minus 2 gives us a positive 1 formal charge. And then when we get to the next oxygen, the one on the right, we again have 6 valence electrons for oxygen, minus 1/2 of the bonding, which in this case is 2 for the single bond there, minus the 6 that occur in the non-bonding pairs. So that's a total of minus 1. So on this molecule, we have a +1 charge for the central atom and a -1 charge for the right-hand terminal oxygen. So the total charge for this molecule is a net 0 because we have a 0, a +1, and a -1. So the net charge is 0. But it tells us where there's higher electron density and lower electron density on our molecule. So now that we kind of understand how to do this, what are the rules? Okay, so not all structures are created equal. And resonance structures here, this word just means when we can sort of distribute the double bond in a couple of places, the resonance hybrid is going to be weighted towards the one with the most favorable resonance structures. And there's two rules here. The dominant Lewis structure is going to have a formal charge closest to 0. So we basically want to minimize formal charge. And if we have formal charge on the molecule, we want to put that negative charge on the most electronegative atoms in the structure. Okay, so let's look at an example of what I mean. What are 3 possible Lewis structures for a thiocyanate ion? We have NCS-. Okay, so let's calculate our valence electrons here. So for nitrogen, we should have 5 valence electrons, plus carbon, we should have 4, and sulfur, we should have 6. So that should be a total of 15 electrons, plus we need to add in 1 electron for the charge on the ion. So we have 16 electrons to work with. Okay, we're going to come up with our skeleton structure here. And here we're going to put our least electronegative in the center. So if we look at the periodic table between carbon, nitrogen, and sulfur, carbon is furthest from fluorine. So we're going to have a carbon in the center, and we're going to surround it with a nitrogen and a sulfur. It doesn't really matter what side this comes on, but I'm going to do it as it's written in the formula. Okay, so we had 16 electrons. We're going to subtract out the bonding. So here we had 16 electrons. We're going to subtract out 4 electrons for bonding. So that means we have 12 more electrons to distribute to this molecule. So we're going to start with the most electronegative first. So nitrogen is more electronegative than sulfur. It's one of those highly electronegative atoms. So we'll start by putting as many as we can around nitrogen. We have 12, so 1, 2, 3, 4, 5, 6. We still have 6 more, so 2, 4, 6. And the last thing we need to do is satisfy the octet. So here we need to create double, triple bonds in order to satisfy the octet. So here's where we have a couple options. We have a couple options here. Let's look and see what those could be. We're going to write them over here. We could take 2 lone pairs from the sulfur and 2 lone pairs from the nitrogen, and we would get a double bond at each, and then 2 lone pairs of electrons on each nitrogen and sulfur. That is one possibility. Okay, another possibility is that instead of creating 2 double bonds, we create a triple bond here and a single bond that still satisfies the octet for the carbon, but it leaves us with an unequal number of bonds and an unequal number of lone pairs of electrons on the molecule. So that's another option. And then our third option could be here, where we make a triple bond to the sulfur and we leave all of the non-bonding pairs with the nitrogen. Okay, so now we have to make a rational decision about which one is the best structure and why. So we need to calculate the formal charge. I'm going to show you a shortcut here that I really like that helps do what we did on the previous slide here with this formula here, and just does it in a very visual way. So one really easy way to do this is to draw a box around the whole molecule and then take and bisect the bonds in half, okay, like this, and then count the number of electrons or half of bars that are in the box. That's the formal charge. So it's doing exactly what we're doing. We're taking the number of electrons you should have, and we're going to subtract out the number of dots or half bars in the space. So nitrogen should have 5 electrons, and we have 1, 2, 3, 4, 5, 6 spots here inside the box. So we have 5 minus 6. So 5 minus 6 is minus 1. So the formal charge on nitrogen here is minus 1. For the central carbon, we should have 4, and we have 4, so this is 0. And for sulfur, we should have 6 valence electrons, and there are 6 inside the box, so that is also a 0. Okay, so let's continue this kind of process for each of these possible structures. Okay, again, nitrogen should have 5, and in this case it has 5, so that's a 0. Carbon should have 4, and in this case there are 4, so that's 0. And sulfur should have 6, and in this case it has 6 in the non-bonding and half of that bond between the carbon and sulfur, so this is minus 1. Okay, and the last one. Sorry, I'm getting a little bit out of space here. Okay, so again, carbon should have 4, and it has 4, so that's 0. Sulfur should have 6, and it has 5. So we have 5 minus 6. This is minus 1. And nitrogen should have Nitrogen should have 5, and it has 2, 4, 6, 7. So 5 minus 7 is minus 2. So here, sorry, this should be a plus 1. Sulfur should have 6, and it only has 5, so it's plus 1. I'm sorry about that. So here now we have to decide which is the dominant structure based on the formal charge. Okay, so we've got to think about each of these possible structures. We want to pick the one where the formal charge is minimized. Well, that gets rid of the third option here. We have a 2 minus and a 1 plus. This is not the most minimal formal charge, so we're just going to cross that out. So this is not the option here. Now we have to decide between these two. Okay, so in these two we have a negative charge residing on a sulfur or a negative charge residing on a nitrogen. And nitrogen is one of the NOFs, the most electronegative atoms. So the first structure here is really the dominant Lewis structure. This is the one that we are going to put as the right Lewis structure. They're all right, but the best one is the one where the formal charge is located on the most electronegative atom. So if we want to just clean this up, we would end up with this structure. Here. Okay, let's do some more examples. Draw the possible Lewis structures for CO2 and assign formal charges to decide which is the dominant structure. Okay, so again, carbon dioxide, we need to count the valence electrons. Okay, for carbon, we have 4 valence electrons. For each oxygen, we have 6, so that should be 12. There's no charge here, so that's the total number of electrons. We have 16 electrons to work with. All right, now we want to draw the skeleton structure. So here, the skeleton structure for carbon dioxide, carbon goes in the center, oxygen on either side. Oh, I'm sorry, I'm getting ahead of the game here. Ignore that. Skeleton structure. We're going to put carbon in the center, oxygen on either side. Sorry. Now we want to subtract out our bonding, so we have 2 bonds, so 4 electrons for bonding. So 16 minus 4 means there are 12 electrons left. We're going to distribute it to the outermost electronegative atoms first. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Well, that's all of them. Okay, so now all of the electrons that should be distributed to the molecule are distributed. The next step is that we need to look and see if our octet is satisfied. And so we look here, and for oxygens we have 2, 4, 6, 8. That's good. We can do that. But for carbon we only have 2, 4, so that does not work. We need to increase our bonding order here and share more electrons with the carbon to satisfy the octet. Okay, so we have some options again. Here we can take and make a double bond here and a double bond here. We could also, right, if we have an alternate, we could take a double bond here and make a triple bond here. That would also satisfy. So which is the correct? So now we got to do those possibilities and think about the formal charge. Okay, so again, I'm going to redraw the possibilities over here. We have carbon with a double bond to oxygen with 2 remaining lone pairs on each. Or the other option is oxygen triple bond to carbon with a single bond, like so. Okay, so here we need to again look at formal charge. We could also make the triple bond on the other side, but it's effectively the same. It's just a mirror image of this one, so we don't need to do that one. And so here we're going to draw the box around and start looking at formal charges. Oxygen should have 6 valence electrons. There's 6 charges inside the box, so that's 0. This is also 0. Carbon should have 4. It has 4, so that's 0. So there's 0 formal charge on this one. Let's look at the second option. Okay, so here, oxygen should have 6 valence electrons. We're going to subtract 5, so we have a plus 1 over here. We don't have quite enough. We have a 0, and here we should have 6, but we have 7, so that's minus 1. And so the dominant Lewis structure then is going to be this one here, because the formal charge is minimized. All right. Let's keep on to the next one, ozone. Let's look at resonance structures for ozone. This is the one we did before. But let's draw it out. So again, 3 oxygens, so each oxygen should have 6. So we have 6 electrons times 3 of them. There should be 18 total electrons in this structure. We're going to put an oxygen in the center, 2 oxygens on the outside. We subtract out 4 for bonding. And that leaves us with a total of 14 electrons left in our structure. We come over here and we put them on the terminal atoms first. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, but I still have 2 more to go. So the other 2 have to go inside on the internal oxygen, central oxygen. Again, I look at this and I look for an octet, and the outer oxygens have an octet, but the inner only has 2, 4, 6. So we need to create a double bond. And so I have some options here. Here I could take a lone pair from the left-hand side, or I could take a lone pair from the right-hand side. And if I look at this, they're both exactly equivalent. How do I decide which one I do? And so in this case, what we get are 2 structures which are similar. We get oxygen double bond, oxygen single bond. And we also get the other side version where we get oxygen single bond, oxygen double bond, oxygen. And so in terms of formal charge, there's no advantage or disadvantage to these 2. And so when you have equal structures that are equally as likely, what we do is call this resonance structures. True resonance when they can really be in both of these at the same time. And so what happens is this double bond here in these structures, here and here, just transfer back and forth because it equally wants to be in both positions at the same time. And so how we draw this is that we draw a double-headed arrow indicating that it is going back and forth between these. And so typically, instead of stacking them on top of each other, we would draw it like this. And we would put our lone pairs in here, so oops, and I'm missing a pair here. My fault, I forgot these up here. Okay, and then we would draw a bracket around these to indicate that they are resonating between the 2. Another way that we sometimes see this is that we'll draw it as one structure, and we will put this sort of dashed bond between the 2 to indicate that this is a partial double bond at each oxygen. And we can't draw this one with the lone pairs because it wouldn't make sense, because we can't put them in both locations at the same time, but this indicates that there's a little bit of double bond character at each oxygen. So this we call the resonance hybrid, where it's showing both at the same time. Okay, let's go to nitrate and look at the nitrate ion here. Again, we have nitrogen, which should have 5 valence electrons, plus 3 oxygens, which should have 6 valence electrons, plus 1 electron for the charge, which gives us a total of 18, 19, 24. And so for 24 electrons, When you think about this structure, nitrogen and oxygen, nitrogen is further away, so we're going to have a nitrogen surrounded by 3 oxygens. And now we have to subtract bonding, so -6 for bonding. That gives us 18 electrons to distribute. Go back over here and start adding them in. 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay, so now all of our electrons are distributed. We look for an octet, check for an octet, and we see that nitrogen only has 2, 4, 6 electrons. It doesn't have enough. So we need to create another bond to give nitrogen an octet. And so here we have options, right? We have options. We can do this as number 1 option. We could do this as number 2 option, or we could do that as 3 options. So now we need to show all 3 resonance hybrid structures. So we could show it here by showing oxygen, double bond nitrogen, okay. Double-headed arrow to the next option. Whoops, just 2 there. And then double-headed arrow again to the third option. Whoops, let me give you some space. So all 3 of these are valid structures, and the last thing we would want to do is put a bracket around it and put a -1 charge to indicate that all of these are negatively 1 charged. Again, if we want to show the hybrid version of this, we would show, we'll do it up here, nitrogen, oxygen, 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 and we would show a partial double bond at all 3 locations. This is where I want to stop. We'll come back to the end of this and rehash any questions you have, so write down your questions. And on Monday when I get back, we will discuss any of those questions and finish out this chapter. Thanks for listening.